Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are a student from MCTA 3352, Industrial Automation. We'll be discussing for PLC system, simulation analysis and logic development for a smart conveyor system that we built. My name is Muhammad Farish Iskandar bin Muhammad Shahidin.
My name is Muhammad Fahim bin Ahmad Nurishan.
My name is Muhammad Irfan Fahmi bin Ahmad Usri.
And my name is Amir Iman bin Makir. So, the introduction for this will be, we are doing a weight storing system using a conveyor belt. And essentially, if an item is detected and it is overweight or underweight, it will go through a filter which will detect it and filter the items to its respective storing system. This utilizes real-life data making decision. It uses weight sensors, and we use some components that ensures high quality control.
So moving on to the ladder diagram. So basically, this system is one of the system that we built ourselves. So one of the main thing about this system is that just like my friend said, is it detects whether the parcel or product is overweight, underweight, or perfect. So if it is perfect, it doesn't go through any motor. Okay. So the first one, we need to see about how this ladder diagram works. So basically, as you can see here, we have the motor start and motor stop. So this line is basically the first line that contribute to the motor option, which is whether the motor is start or motor is stop. So if we press the motor is start, basically we'll go here, then it will latch here. So basically it automates the motor. Next one, we can see here, which is the comparison and also not the comparison, but the arithmetic operation. So basically, we want to change between, as you know, that the pressure sensor of system, the maximum is 32767. That is just a byte number, which is a number, a constant number. I want to change the number into a gram. So basically, what we do is that when the sensor detects, it will go through a series of equation, which is the weight that we get, the raw data that we get, the divide by 32767, then I will multiply by 5,000, which is the max for the gram, 5,000 gram. Meaning that if we go to the new weight, it will go to here, a series of option. The first option is overweight, the second option is underweight. So if it's greater than 2,500 gram, it will go over here, which is can activate the diverter 1. But if it's underweight, less than 2,500 gram, it will go to here, which is activated the diverter 2. So the next one is the ladder diagram variables. So as you can see here, all the variables here are stated: the motor start, the new weight, the light, the sensor, the weight, motor, diverter 1, diverter 2, and the time. So basically, as you can see here, all of them are bool. The bool one is whether it's true or false. So the motor start is basically a button. Next one, we can see here the no weight, the weights, and yeah, the two things here basically contribute to the constant value, which is can change. Then we look over here, which is the TOF. TOF stands for timer off, which is the timer of delay.
So now we come to the arithmetic and comparison. We have four type of arithmetic and comparison that we use, which is division, multiplication, less than, and greater than. For division, we divide it by 32767 because as my friend has said, it is the maximum number that can be used for a 16-bit signed integer. So if we do 32768, it will be negative. And then for multiplication, we just divide it by 5,000. We don't really, it doesn't have to be 5,000, but we just choose it to be 5,000 because we don't want it to be too complicated. and it will be based on the greater than. So since we are using multiply by 5,000, our greater than must also be a minimum 5,000. It cannot be more, it cannot be less.
Next, we go to the timer, just like what Brother Amirul as well as Brother Faris have explained in the ladder diagram as well as the arithmetic components, in which you can see that we are using TOF0 and TOF1, which stands for timer of delay. If you go back to the ladder diagram, you'll see it after the greater than the lesser than. If you see that greater than, lesser than, and then you have a timer of delay. The reason why we're doing this is because timer of delay is designed for an immediate response. If you go by timer on, I think it is some sort of, you have to press that for certain amount of time for it to uh, do some sort of an response. But for timer of delay, you once it goes into that instruction, it will give you an immediate response. So in this case, when the weight exceeds 2500 gram, the diverter will immediately activate to push that box into a certain bin, which we can say is a rejection bin, even though it's not really a rejection, but we assume it that way. So when the item moves and the weight signal drops, the off delay timer overrides the shut off, keeping the diverter active for an additional 1000 millisecond, which is 1 second, just to keep it back, the whole conveyor. So that it ensures that the arm remains extended to fully clear the item from the conveyor belts. So in that slide, we have explained the symbol, present time, function, and so on, and as well as how does it work in this specific circuit in a simplified explanation. If you can read it, that is all.
Now I will explain the recommendation. So first of all, our current PSC based sorting system is functioning well. It can detect underweight, good weight, and overweight. But it has more potential to enhance its efficiency, reliability, and data visibility. Therefore, the first recommendation is to integrate a real-time production dashboard. By connecting weighing sensor and diverter status to Internet of Things gateway, you can simulate all operational data in HMI or cloud dashboard. Allow supervisor to monitor the number of items sorted, their status, and error condition instantly. With this feature, operator can identify issues faster, reduce troubleshooting time, and make better production decisions. Second recommendation is smart sensor feedback and predictive maintenance. In many conveyor systems, mechanical breakdowns occur due to wear and tear that goes unnoticed. By adding vibration sensor, current sensor, or temperature sensor to critical component, the system can analyze data and predict when motors, diverters, or belt require maintenance. This prevents sudden downtime and reduce maintenance costs in the long run. Next, we recommend using data logging for quality control. Every weight measurement and sorting result can be recorded automatically and stored in a database. Over time, the data can show trends such as increasing faulty products or change in product weight pattern. Quality engineers can use this information to identify problems in upstream processes such as packaging error or material inconsistencies. Lastly, the system can be improved with an IoT-based alarm notification system. In case of diverter fail, conveyor stop unexpectedly, or the weight reading goes out of balance, the system can send an instant alert through the email or mobile app. This helps the technician respond immediately without needing to be physically near the machine at all times. Now I will explain the conclusion. In conclusion, throughout this project, we have successfully demonstrated how a PLC-based automation system can classify products based on weight using sensor, comparison instruction, timers, and actuators. The system is designed to detect three main categories: underweight, good weight, and overweight items. Each category is linked to a specific diverters, which redirect the product to the correct lane. The ladder diagram play a crucial role in this operation. Rung A handles underweight product. Rung B manage overweight item. Rung C process product that fall within the acceptable range. For each condition, corresponding timer is activated to ensure that the diverter stay open long for the item to be directed safely. This demonstrates how PLC logic combines sensor decision making and timing to achieve reliable and smooth automation. The simulation also shows the importance of correct sequencing and logic arrangement, which input and output work together to form a complete control process. From the weighing sensor to detecting the item to the PLC comparing the value to the diverter activating at the right moment, the system effort operates in a coordinated and systematic manner. This minimizes human error, improves throughput, and increase consistency. Another key takeaway is that timer and comparison block are not just basic PLC functions. They are essential tools that help maintain accuracy and stability in real-world industrial automation. Without precise timing and correct logic evaluation, the system will not be able to function correctly and efficiently. Overall, this project highlights how the system achieves consistent, repeatable, and efficient sorting, minimizing human error while improving throughput. When combined with an Industry 4.0 enhancement such as smart analytics, predictive maintenance, and real-time monitoring, the system has strong potential to become a fully intelligent and highly optimized automatic sorting solution in the long run. And that's